This is for General Maths Spec and it is Circle Geometry in 8.6. Remembering some main terms. A chord is a line that goes from circumference to circumference. An arc is around the circumference from one point to the other. Remember there's two arcs here. There is the minor arc. There's also the major arc. A sector is sort of like a piece of pie. There is a minor sector as well as a major sector. And a segment is created when a chord is on a circle and you have a minor segment and a major segment. Degrees in this chapter are basically measured in radians. We can actually measure angles in degrees or radians. A 90-degree angle would be pi on 2 radians. One full revolution would be 360 degrees or 2 pi radians. A small c indicates a measure of radians. However, if the angle is given as 2 pi without the symbol c, we know that that's going to be a radian measure. To convert from degrees to radians, you multiply by pi divided by 180. For example, 90 times pi on 180. 90 goes into that twice, gives you pi on 2. And to convert from degrees to radians, 90 degrees times 1. To get from pi on 2 times 180 on pi, the pi cancels and that goes into that 90, so 90 degrees is the angle. Okay, three main formulas that come out of 8.6. An arc length, remember, theta is measured in radians. An arc length, if we had a full circle, then the distance would be the circumference, or 2 times pi times radius. If I had half a circle, it's going to be a half times 2 times pi times radius. When I have an arc that goes from there to there, then I've got this fraction of a circle, and that fraction will be theta out of a full revolution, which is 2 pi, so it's going to be a length of theta on 2 pi times 2 times pi times radius. The 2 pi's cancel to leave theta times radius, and there's my theta times radius. Length of a chord. Remember, theta is always measured in radians. If I have my circle and I have a chord, that is the distance of the chord x. If I consider the radius and the radius, that would form that triangle, and this is the angle between those two radius that forms that chord. So I'm going to consider the right angle triangle where that's r, that's x on 2, and that's theta on 2, and that's a right angle triangle. If this is my angle, this will be opposite, this will be hypotenuse, therefore I'm going to use the sine function. Because of SOHCAHTOA, if I have opposite and hypotenuse, I would use sine. So the sine of the angle theta on 2 will equal opposite, which is x on 2, on hypotenuse, which is r. Sine of theta on 2 equals x on 2r, and x will equal 2r sine theta on 2, which is what my rule was. Area of a sector. Remember, theta is measured in radians. The area of a full circle would be pi times radius squared. The area of half a circle will be half times pi times radius squared. The area of a sector will be whatever proportion of a full circle, which will be theta divided by 2 pi times radius squared. The pi's will cancel to leave 1/2 theta r squared, which is what the formula that's given is. And lastly, the area of a segment. If I have a full circle, there is my segment. That area is going to equal the area of the sector minus the triangle. So it's going to be the sector minus the triangle. The sector I know from above is a half r squared theta. I need to work out what the area of the triangle is. Now my triangle is r, and that's theta. I know that the area of a triangle is a half a times b times the sine of the included angle, which in this case will be a half r squared sine of theta. So I have a half r squared sine theta, common factor of a half r squared theta minus sine theta, which is what has been given.